The name of this video is Volume Polarization Charge Part 2. In fact, in this video, finally, we will manage to understand the physics behind the polarization charge in the volume that is rho p. Sigma p, we already qualitatively understand it. Now we qualitatively will understand rho p. Now, I will resketch one more time the little sketch I had here in the previous video, which I know causes lots of problems, and so it's worth to repeat it one more time to make it even bigger. And it's also useful to connect it to the next part of these videos. I need to interconnect these two videos. So in a big dielectric solid, again, let's consider within this solid, and now we will eventually extend to the entire solid volume. We have a small interface. And so this interface, as I sketched in the previous video, let's say that this interface is this area here. So this is the 2D version. So this actually, if I were to look at it in front, it's a little disk with an area delta A, okay? So this is our area delta A seen from this side. I want to compute the total net charge that goes through this interface during the transient, from the beginning to the end of the transient, which happens when I switch on the external field V naught that generates polarization. All these molecules start to be rearranged, they get stretched, and so charge will cross, positive charge and negative charge will cross this area, because the molecules get stretched, okay? So it has to cross, okay? This eventually will lead to the concept of rho p. All right, so as we've seen the other time, we use this concept of slanted cylinder, where this one is the portion of the cylinder this one is on the left-hand side. So I'm redoing again the sketch we already had done in the previous video, but I'm aware that this sketch causes lots and lots of problems, so it's worth repeating it one more time and connecting it to the rest of this video. Okay, great. So, as we've seen before, a positive charge somewhere here will definitely cross during the transient because it is associated with the stretching of its center of charge by a quantity which is actually this quantity here eventually. So let's start here, is this quantity here, which is L plus the displacement associated with the positive charges in the molecule. This definitely crosses. This is the last one in space to cross. It just barely makes it through the barrier, through this surface here, which I remind you, this region here is associated as a matter of fact with an area delta A, and this eventually makes a volume delta B, capital delta B, my small volume, okay? So, but I'm looking in 2D. All right, what about the negative charges? So this will be eventually the vector L minus, okay? And so a negative charge sitting somewhere here, right at the boundary, it gets stretched, so it definitely crosses this region of space by this amount, so it will cross in this fashion here, okay, where this quantity is L minus the displacement associated with the negative charges, okay? The last charges to cross are those somewhere in this region here. So all and only the charges within these two volumes, which we called in the previous video delta V plus and delta V minus respectively, only those charges really will cross the area delta A during the transient, during the polarization phenomenon. Now in particular, so let me resketch again, just to fix ideas one more time. So this one is L minus vector, and this one is L plus vector. L plus and L minus, as we already said several times, in general can be different from each other. They can also be the same, depends on the molecules that you are considering. All right, given all that, what is the total vector L? So let me specify it one more time. The total vector L is actually this vector here, which, as expected, so this is my vector L, which is L plus minus L minus, it points in the direction of the electric field, which we know in this case, it polarizes the dielectric material in this direction. So this is my field E naught, okay? So these are all parallel lines. They're all parallel lines. On average, we know that the dipole moment, which points in the same direction as L, so these are all parallel, just jitters around because of temperature. But that's exactly what we get. And in the previous video, we also defined this point here. It's the center of charge, capital Q, and the normal unit vector, it's N, pointing in this direction. Great. This all makes sense because the positive charges follow the field lines, the negative charge is opposite to the field lines. So now all these molecules get stretched, and so they cross, like this one crosses like this one crosses like that, all these charges cross this area. We computed the overall charge across the entire area, and we know that this the flux of, it's nothing but, let's write it down here, dQp, the polarization charge crossing delta A, it's nothing but in the limiting case, of course, the delta A becomes a dA, is P, the polarization vector, dot dA. So it's the flux of P through this area in the limit that, of course, delta A becomes eventually a dA. Great. All right, and remember the previous video where we discussed exactly why this happens and why we need to use this lengthed cylinder, why everything works out because there is an angle theta, and that's what allows us to find the height of this cylinder, which depends on this angle theta, which I'm not going to sketch here. I just wanted to sketch the physics in particular of this problem and all the notation so we have it clear and in front of our eyes. Now, with all that in mind, suppose that we do have, now this one is a very magnified scenario, is a very magnified region around in the neighborhood of point capital Q, and now let's make it a little bit smaller down here. So suppose that we have an object capital omega, so this is this is our entire dielectric material, okay? It's a full solid, it's homogeneous, it's made from the same material, and within this object, what we are going to do, the whole thing, everything within this capital omega is actually made from a dielectric material, okay? So it's all full and made from a dielectric material everywhere here. Within this object, I consider an inner object. You will see for what reason now. So let's say that the inner object is something like this. And this object, let's call it a capital gamma. So capital gamma is entirely included in capital omega, which is entirely made of the same material, so it's homogeneous. So there is material everywhere. So this capital gamma, which is characterized by eventually a surface capital sigma, which is the boundary between capital gamma and capital omega, is this surface here, is my capital sigma, all right? It's nothing but a geometric construction, and I will see why I need it, but it's just representing an inner region within capital omega, so it's smaller than capital omega. Great. It is worth defining a normal unit vector, as always, associated with the surface capital sigma. So if I take an infinitesimal area element here, of area dA, its orientation will be given by n, which we choose to point from within capital omega to within the rest, which is, from within capital gamma to the rest, which is capital omega minus gamma, which is this region outside, okay? Points outside capital sigma. It's just a definition, and that's what we used, okay? We want to use here. All right. So now, what happens when the electric field E naught is equal to 0, that is, before initiating the process of induced polarization? So what happens in that case? So suppose I want to compute the charge dQp. So basically now what we're trying to do here is the following. This area dA happens to be exactly, for example, the area associated with this infinitesimal element. So these two areas are exactly the same. So this area here happens to be this area here. Therefore, this point happens to be capital Q. Okay? So this area is dA, is the same dA in the limit, of course, delta A becomes dA. So this area is the same, and so this point Q's are all this point on this surface capital sigma. So now I'm considering continuum of these dAs, which when put together, that is integrated, generates capital sigma. So this boundary, capital sigma, is made up of all these infinitesimal boundaries of area dA in the limit, okay? So when you close them up, they create this closed surface. And why is that? Just to give you a sort of sense why I'm doing that, because I want to compute by means of a flux the charge that goes inside this region, capital sigma, just to see if there is a charge within the volume, okay? That's why within, that's why this applies, capital gamma is smaller than capital omega, because I want to compute the charge that migrates effectively the net charge going inside this region of space, which again, I can do by integrating all the net charges, the QP that we know how to calculate for each area dA. Okay, so I just integrate the entire surface, and that's what I get. That's why we do this. And again, the reason why is within capital omega is because I want the charge in the volume. Rho p is what I want to investigate. So in the case E naught is equal to 0, in this specific case, it so happens that the polarization vector P at any point Q, how do we compute it? Well, on average, we can compute it as capital N, the number of molecules, times the mean value of P, the mean value, the average dipole moment, divided by delta V. Is delta P over delta V, okay? So this N over delta V eventually allows us to rewrite this P vector, in this case, in this first case, as this quantity here, we call it the density of molecules, small n. So small n times the mean value of P. But what is, in this case, this quantity? Well, this quantity, in the case of zero polarization, it has to be equal to 0, which implies that, accordingly, the net charge, dQp, which is given by P dot N dA, has also have to be equal to 0. There is no polarization, of course there will be no charge, since this is true for each of these areas dAs, it is true for the entire surface sigma. I don't polarize the system, of course no charge enters this capital sigma, which should be also qualitatively quite clear, which simply means that the entire charge Qp, since the Qp is 0, when I integrate, the entire charge Qp integrated is also equal to 0. I don't need to perform the integral because each of them is 0. What happens, on the other hand, in the more interesting case, when we switch on an E naught, which now happens to be different than 0, so I initiate a polarization phenomenon. So now there will be a net charge, okay, all the molecules in the vicinity of each point capital Q on this surface capital sigma will start to get stretched, so eventually there is a migration of charge within this object. And so if I use capital sigma as my reference surface, the reference I'm interested in, there will be some net charge eventually crossing this region. There will be a charge crossing this region. So the key word now here is that I want the crossing of this charge from where to where. That's the critical part here. I want the crossing of the charge from the negative volume, which is capital omega minus capital gamma. So from this region into capital gamma. So from this region into capital gamma, from this region into capital gamma, etc., etc. This is the charge I want to compute. Inward capital gamma, which is opposite to n, which is the chosen direction, which is always pointing again away from the closed surface we consider. So we are considering a flow of charge from outside to inside, okay, capital gamma. So I want to compute, in other words, I want to compute QP from the negative volume, which is capital omega minus capital gamma, that is all this volume outside, to where? To capital gamma. Opposite with respect to n. So what is the result of this calculation here? Since we are going opposite with respect to the chosen direction of n, I want to see the charge which goes inward, there must be a minus sign, because we are going against n, okay? So if I wanted to compute the charge exiting capital omega, capital gamma, which I can, then I would consider a plus sign, but we are considering the charge going in. Okay, so this is minus, and now this is a sort of Gauss's theorem, right? So we want to compute, we know that this dqp is the flux of P, so it's like a kind of a Gauss's theorem for P. So it's going to be the surface integral on capital sigma of P dot NdA. Kind of a Gauss's theorem, all right? With the minus sign dictated by the fact that I want the charge going in, considering that n points outside. Okay, so minus sign, typical mistake. This minus sign is there for this very reason. And so I'm basically attempting to use a sort of the charge conservation principle, okay? So what is going on, physically speaking, here? So what's going on is before I switch on in hot, there is nothing going on, of course. There is no transit happening. All the molecules are like, if they're non-polar molecules, on average, they don't have a dipole. That's it. Nothing really happens. Now I switch on the field, so there is a transient during which charge migrates and so start to appear inside gamma. So whatever appears inside capital gamma. So whatever appears inside capital gamma is a charge which wasn't there before, and so this is the way to compute it, okay? Whatever appears inside capital gamma is the charge going from outside into it. So you cannot just arbitrarily choose the signs, because you really want, from the physics of the problem, understand what is the charge appearing inside capital gamma. So it goes from outside to inside, minus sign, because n points to the outside, as always. This is just a convention of the sign of n, okay? But this is a very important sign. We will keep these conventions throughout this course, and if you make a mistake with this sign, all the results of all the problems you will attempt to do, they will be wrong. This sign is absolutely critical. All right. So now that we know that, for example, in Piazza, I would ask you to compute exactly that. So as an exercise, even though I kind of already gave you the answer, but I think it's worth repeating this for you. So you should compute the charge QP. So I will compute this. I want you to compute the charge QP going from capital gamma, exiting capital gamma. So going from capital gamma to the negative volume, which is capital omega minus capital gamma. What is this quantity? Please calculate it in Piazza. In addition, I already told you that this is a sort of charge conservation principle. Another question that I have for you on Piazza is, what is the sum of the charge QP, this means exiting, that exits, capital gamma plus that enters capital gamma. And also, if you want, you can play with other things such as the sign of n. You can invert it and see what happens. But this is the standard notation we're going to use. N points outside. Very important to remember that. Definition. All right. So now we are very close to finding the final result of this problem, because we can, by integration, we can simplifying the total charge QP that we are seeking. Okay. So in general, if there is a charge QP, it can always be described by means of a charge density, rho p, function of q, which we integrate over dv over the entire region, in this case, capital gamma, that we are considering here. All right, this is always possible. These just definitions. Now, the physics of the problem comes here. It's this one. We know that QP is the flux of P dot NdA. That's the physics which we derive from this argument. And so it's minus, not to forget it, the surface integral on the boundary of capital gamma, that is capital sigma. And this is what? Of P dot NdA. Now here, immediately, something should you should remember something. Whenever you see something like this, obviously you need to use the divergence theorem. So by means of the divergence theorem, the H for theorem, we know that eventually QP, the polarization charge entering the volume, is given by this volume integral on capital gamma of rho p dv equal minus the volume integral, I use the divergence theorem, over gamma, capital gamma, of the divergence of p dv. Now, since gamma is arbitrary and fixed in an inertial reference frame, if it wasn't fixed, it would be complicated. Arbitrary and fixed in an inertial reference frame, due to the arbitrariness of and the fact that it's fixed, obviously this means that the integrand have to be the same, which means that rho p has to be equal to minus the divergence of p polarization vector. And guess what? This is exactly the same expression we had, or very similar to the expression we had once upon a time for the funny capital P. We said that the rho equivalent was given by minus the divergence. Remember, there was this prime because we had some variables of this vector P, density of dipoles. And this is density of dipoles for molecules, which means for the electric material. So that's the same meaning, if you want. So we already found mathematically this expression in the past, and now we refound it by means of a very solid physics argument, which I really enjoy here, because it's really the physics of how molecules get stretched and how their charge, according their charge is positive and negative, cross a certain area. I integrate it over an entire volume, and I find rho p, which is quite amazing. So clearly, this is the only way to understand the physics of why there is a rho p. And obviously, as we shall see later, there is a connection between E being uniform if E naught is typically, when E naught is uniform, it also follows that P is uniform. It's not always necessarily true, but for most of the materials that we will consider, for all materials, we'll consider this is true. And so clearly, it is clear that if we go back to a uniform polarization, obviously the divergence of something uniform is zero, and there is no rho p, which is the case of that we've seen, which allowed us to understand sigma p, but not rho p. So you need a non-uniform field, of course, plus other boundary conditions eventually. But anyway, at least that, in order to have a rho p, which is given by minus the divergence of p, as we wanted to find out. Okay, so now, to recap this video, we went back to a little infinitesimal surface delta A, eventually dA. There are molecules, an Avogadro number of molecules around that surface, okay, which when they get stretched, they will cross this area dA, left and right, positive and negative respectively. The stretching is given by a plus and a minus, which depends on the material. Overall, the stretch is L, okay, as shown here, which goes along the direction of E naught. And so then this area dA, which is centered around the point capital Q, can be part of an inner surface, which I choose. I can choose whatever inner surface. I could choose another one within a solid object, the electric material, okay? So this surface, capital sigma, then closes a capital gamma within a bigger capital omega, all made of the same material, and points outside capital sigma by definition. The QP from this argument is the flux of P dot n dA, for one single surface, and then I need to integrate it over the entire surface to get the overall charge. Problem is, there is a minus sign because effectively I'm computing the charge which appears inside gamma. Appearing inside gamma, it has to come from outside, so otherwise it wouldn't be appearing. So it comes from outside, opposite of n, minus sign. And so because of that, the total charge can be written, of course, as a charge density rho p over the volume, integrated gives me QP, which is also given by this quantity according to this discussion here. Divergence theorem eventually allows us to find the rho p is minus divergence of p, which is consistent with rho equivalent we found in the equivalent charge distributions of distributional dipoles several videos ago. That's it.